Okay. Now we're still in module 2. This is week number 6. We're still discussing the DC-DC converter. Just let me remind you what we discussed last session. We started with DC-DC converter. We mentioned that we have DC input, which could be anything: rectifier, solar cell, battery, and we converted into another DC, either greater than or lower than the input. Here, let me say 10. I can make it 15. I can make it 5. I call the lowest value to be buck converter, step-down converter. And the upper value, I call it step-up converter, or let me say boost converter. And just let me remind you also that the case is like this. Have a look, and this is the resistance. Here we have switch, inductance, capacitance, and here diode. This is the book. The same elements. This is the input. This is inductance. This is the switch. This is the diode. This is the capacitor, and this is the resistance. You know, capacitor and inductance represent the low pass filter. Diode is the freewheeling diode to have a path for the current, and the switch is the main, let me say, semiconductor switch, which control the circuit operation. We control it using pulse width modulation, as I mentioned before. But at the end, we have switch, we have diode, nothing more, nothing less. Now, today I will talk about buck boost converter, and I will leave Cook and full bridge for the next session to this week, inshallah. So buck boost converter, from the name, it seems to be it's stepping up or stepping down the voltage. Now you may ask, okay, how I choose? At the end, it seems to be I have different options. How can I choose this or that converter? Look to the application. Look to your input and the application. As example, if your application never gonna have a time to be higher than the input, then you go for buck. If you go for higher than the input, you go for boost. If you have some situation, the output, the load need voltage lower or higher than the input, you go for buck boost. So it's a matter of redistributing the components. You see here at the end, I have again switch, diode, capacitor, inductance. This is my load. But how I connect them will change the effect. And also let me remind you that for buck converter, the relationship is D. For boost converter, the relationship is 1/1 minus D. It means this is the step up effect, and this is the this is the step down effect. This is the step up effect. Okay. Now this circuit, as you can see, it works in two situations. The first situation, when I switch the transistor here in this way, definitely current will follow through the inductance. Nothing will follow here. This will be open circuit. How it look like my circuit? Look like this. Current follow here, and the diode is open circuit. Now the energy stored in the inductance. When I open this one, this energy need to be released through the diode. You got it? It's released through the diode. Okay, how it look like the circuit? You see here, the switch is open, energy here release through the diode is here. It's short circuit now, it's conducting. Now, if I want to find the voltage as we did, but by the way, we are following here the same steps, how we discussed the book, how we discussed the boost. Now we will discuss in the same way. I will find the relationship for input voltage with output voltage, and then I will assume that the circuit is lossless to find the current, input current related to output current. Then I go for boundary condition to find formula. Then I go for this continuous. Then I go for rippling voltage. You see the same procedure. The only difference is the values here. Okay. As example, here when the switch is on, here the switch was on, current will follow through the inductance, so the whole voltage will apply across the inductance. Very simple. This is VL, it seems to be, it is VD at the beginning, at T on. Here, from here to here is T on, and don't forget T on is DTS, okay? For T off, from here to here, T off, okay, which is equal 1 minus DTS, okay? Now, it seems to be, this is the T off situation, this is the off situation. This one in parallel with this one and this one opposite in sign, so it seems to be it's minus VO. Very simple. What about current of the inductance? When we switch on here, energy will store in the inductance. So you see the current increase. When you open it, we are here, we open it, current release, increase, release. Okay, you see here? The same discussion before. And definitely inductance current is taking current from the supply and from the return from the output back, which means that the inductance current is equal to both currents. Okay. Now I can't find the relationship of book boost. It's found to be, you see here, V output over V input equal D over 1 minus D. D itself is the book, it's the step down. 1 over 1 minus D is the step up. I can use it in any one of the two methods we used before for book or for boost. As example, I will take example. Let's see the average voltage of the inductance. Okay, have a look here. VD at T on. This is VD at T on, which is DTS. Minus VO at T off, which is 1 minus DTS, T off. Simplify, you got the formula. Very simple. Anyway, this is my formula which I'm going to use in buck boost converter. As we did always, we assume that the circuit is lossless. Input power IDVD equal output power IOVO. Okay. Now I can rearrange VO over VD equal ID over IO. I have this one already derived, I drive it here. So I just need to substitute. This is the formula. I got formula for current. At the end, by the way, you are going to use this formula. Okay, here I'm just showing you how we got it, how we got them. Now, also similar to the discussion of boundary condition, I here added both of them, VL, IL, the previous, let me say, graph. I put them in one graph, okay? And boundary condition, as you can see here, it touch at 0. And we start with the same discussion. IL, by the way, IL is the input current because you see it's connected to the input. This is the input current, I input D, which is following through the inductance. Okay? Is 1 over 2 IL peak, and IL, as you remember, we mentioned that we got it from VL equal D IL over DT. We rewrite the equation again and integrate to find it. We got it here, as you can see. Is TS VD over 2 L D. Now this current I inductance is in terms of input voltage, but I know that relationship between output voltage to input voltage is D over 1 minus D. Can I substitute to find current in terms of output voltage? Yes, I can. Now it's look like the equation becoming this form. Okay. Now just I need to substitute here. It will be VO in term IL in term of VO. Now if I sketch this equation, let me sketch it. Okay, this is D and this is here the current. Okay, IL. Okay, normalized value, usually they divide it by its maximum. Anyway, when I sketch it here, it's line, straight line. It peak at D here equals 0. So if I substitute here 0, I got the highest or the maximum current. I can rewrite the current ILB in terms of its maximum. It is this formula. So it tells me that IL affected directly by D, but inversely by D, because when D increased, IL reduced. And it's clear from the figure here. Okay. The same thing for IOB. IO. We know that IO is IL minus ID. I can also use IL here, substitute and simplify. I got this formula. Again, I can sketch it. By the way, here you can see square. Okay, and there is minus here. Without this one, just only d square, we know this is the parabola. But because we have minus, we expect it will become like this, similar to the exponential of minus x, as we see here, the dotted line. Also, it peak at d equals 0. So I can find maximum, and I can substitute again to find it in terms of IO maximum. Now next, I move to the discontinuous. We mentioned that for discontinuous conduction mode, T on is it the same, okay, which is DTS. But T off from here to here, T off will be divided into two parts. One part is delta 1 TS and the second part delta 2 TS. Delta 2 TS is, we don't take it in consideration because 0, the current, and it becomes 0. Okay, both current and voltage. So I consider delta 1 TS. I have this formula from the previous discussion, okay, and I can derive formula to relate in the same way to relate V out over VD. I also multiply this voltage here by the time and this voltage here by the time and simplify. I go to the relationship between output and input voltage to be D over delta 1. You see here, delta 1 is part of the formula. If I take this and compare it, by the way, if I take this and compare it with the continuous is VO over VD, D over 1 minus D. Just a minute, D is the same, which is the on, because when you say DTS, it's on time. And delta 1 minus DTS is off time, which is delta 1 here, TS. Because you see here, this part is already cancelled. I can rearrange to find D for discontinuous mode, okay, by introducing the two equations together, this one and this one. Then I can find the relationship which relates D to V out with output to the input voltage and output voltage to the maximum current. I will use this formula later on in an example at the end of the discussion. In the same way, when we plot the relationship between normalized current, normalized voltage with respect to D, as you can see here, D change from 0 to 1. This is the normalized current formula, normalized voltage. I can find that these these lines represent the linear, or what we call it, continuous conduction mode, while these curves, the dotted line here separate between linear and non-linear, represent this continuous conduction mode. We also mentioned for this in boost and book, the same thing apply here. Let's take example to clarify the point. In a buck boost converter, he specify buck boost, okay, converter operating at 20 kilohertz. Directly I say, okay, TS equal 1 over 20 because it's 1 over Fs, 1 over 20 kilohertz, and I did the calculation. Inductance is given to you. Output capacitor C is sufficiently large, and VD, which is the input voltage, is 15. VD is 15 volt. Okay. What else? The output is to be regulated 10 volt. Okay. V out is 10 volt. And the converter is supplying a load of 10 watt. PO is 10 watt. Calculate the duty ratio. Okay. Now let's start at the beginning, okay, to find D. Always D is an essential element to be found. Without finding D, we cannot do the calculation. So I don't know if it is continuous, discontinuous, but I started as a continuous, and then I will see. So D over 1 minus D equal 10. I have the output voltage, I have the input voltage, I solve this equation, I got duty cycle to be 0.4. Okay. Now I have the formula for output. You may say, okay, just a minute, where you are taking me? I'm taking you to find the output and to check with the maximum. If it is lower than, this means that we have discontinuous conduction mode. If it is higher than, we have continuous conduction mode. Very simple. Check the boundary. Okay. IO max, I have it. I substitute T, VO, all of them, I have them, inductance. Okay, I got it 5 ampere. And I come to find IO boundary, okay, based on this. So because I have it here, and D, I have it here. I got the boundary current is 1.8. Let's assume this is the boundary current, 1.8 ampere. Boundary current, as you remember, we discussed it. It is the, let me say, barrier or the junction between the continuous conduction mode and below discontinuous conduction mode, which means if my current higher than the boundary current, we have continuous conduction mode. If it is lower than the boundary current, we have discontinuous conduction mode. Okay. Now I got it 1.8. Okay. Let's come to find the current of the circuit. I divided power here 10 over the voltage 10. It gives me 1 ampere. So the circuit current is 1 ampere. Now you tell me 1 ampere is lower than 1.8 or greater than 1.8? You tell me.
Lower.
Lower. This means that this is discontinuous or continuous? Which one?
Discontinuous.
Excellent. We are working in the discontinuous conduction mode. Just a minute. Let me back to the question. What do you want me to find? Calculate the duty ratio. Now I discovered that the circuit is discontinuous conduction mode, so I will use this formula. I have it. I just need to substitute. I have VO, I have VD, I have IO max. I substituted. I found to be 0.3. Very simple. Now, last point here is the, you remember I talk about rippling voltage because have a look. Yes, we have battery at the input, which give me smooth DC. But the output, we may see it in this way. But if we zoom it, we can't find there is ripple. It's difficult to have, let me say, zero ripple. Usually there is ripple. It could be 0.5% or whatever it is. But it's written on the nameplate of the device. When you purchase device, it tell you the nameplate, tell you the type of converter, the specification, the switching frequency, okay? And so the ripple in voltage. And if you want to design, you need to specify how much ripple you accept for your converter. Now, if I sketch the diode current, the diode current of the circuit, you remember we say at the beginning the switch is conducting, diode will be open circuit, so zero current will follow. And when the switch is open circuit, the diode will conduct. It will conduct the inductance current, and then we can see is decrease. Inductance current is going to decrease. Now this is IO, which separates these two areas, which represent the charge we store and release in the inductance. Now what I want to find, I want to find the ripple in voltage. I know that Q equal CV, or in another way, V equal Q over C, as you can see here. Ripple in voltage equal ripple in charge over C. Now ripple in charge, I will take this rectangular, from here to here is T on, which is DTS. And from here to here is IO, so I substituted here. I remember IO based on ohms, say it is VO over R, so I will substitute VO over R. And usually in RC circuits, we multiply RC together and we call them tau, the time constant of the circuit. While in inductance, it will be L over R, tau will be L over R, as we learn in level 1 and 2. Now the circuit, the relationship become very simple relationship, which give me dTs over tau. I control tau by controlling the capacitor. I control the ripple. The circuit here, its application is clear. Use in PV. In PV we can use it because why? Do you know why? Because in PV the solar radiation is variable through the day. It's go up, go down. Okay. So based on this, the voltage I produce from the PV photovoltaic from the solar cell is also variable. But we want to supply it to load. So what should we do? We use this buck boost converter. If it is low, step it up. If it is high, step it down. At the end, the load receives smooth, specific voltage. The same thing could be said when we charge the battery. The battery, it's not preferable to charge the battery with variable voltage, power current. No, it's preferable to be constant because look, this affects the life of the battery. It may be die early. So to make it work for long period of time, we need to make sure that how we charge them, the way of charging, the way of discharging itself also affect the life of the battery. And definitely if we have AC, we can connect inverter. The next topic to be discussed, inshallah, after in week 8, sorry. And then we provide the AC. Sometime, okay, the battery not only charged by the DC-DC converter, the buck boost, but also from a rectifier. We can charge it, helping in charging. They can share the charge. As example, rectifier could work at night to charge. Okay, at night, because there is no solar radiation, the PV will not provide voltage, power, current, and so to charge the battery. So rectifier will work. I will stop at this point, and if you have a question,